Welcome back to Codex. Today we're happy to feature a talk from Nick Trefethen of Harvard University. Professor Trefethen is an expert on numerical analysis, numerical linear algebra, approximation theory, and approximation practice. Today he'll be speaking about analytic continuation and the one-wavelength principle. Take it away, Nick.
Okay, thanks very much. I haven't been at a Codex seminar before, so it's fun to be here. Thank you very much. As a bunch of you know, I love the complex plane, so I'm sort of an applied complex analyst and approximation theorist, I guess you'd say. And the talk today is certainly about the complex plane. The subject of analytic continuation has a theoretical side, but I'm a numerical analyst, so I will certainly be mixing theory and numerics. And you can see from the table of contents there, I'm going to mix together a few things. So let's go. So to begin with the pretty gloomy theorems. So let's suppose we have a function f, and we have another function f tilde, and they're defined and analytic in a region omega, and we're interested in something we know about them on a subdomain E. So we all know that if they're equal on E, two analytic functions that are equal on E, then of course they have to be equal everywhere on omega. So that's classic theoretical complex analysis. But it's also true that if they're merely almost equal, then you know nothing. So it's a theorem that if f tilde minus f is smaller than epsilon on E, nothing whatever can be inferred about their difference at any other point. So I won't go through a proof, but this is standard complex analysis in effect. Approximate analytic continuation is in some sense completely impossible. That's what this theorem tells us. So you can't get gloomier than that. It's completely impossible unless you know your function exactly. However, so the question is, why do we get so much done in practice on computers? And nobody really knows the complete answer to that, but a part of the answer comes from theorems like this. Suppose you know that you have two functions f and f tilde that are bounded on the domain omega, and it's convenient to suppose they're small enough. Well, then you can infer something. If they're close together on E, then they have to be close together throughout omega, and the quantities involved are epsilon to fractional powers. So we have to stare at that for a minute. So we suppose f and f tilde agree to epsilon on the subset E. The question is, how closely will they agree on the rest of omega? Well, of course, they can't be as further apart than 1, because by assumption, they're both smaller than a half. So how far apart can they be? And the answer is epsilon to fractional powers that depend on where you are in omega. So within E, it's epsilon to the 1, and on the boundary of omega, it's epsilon to the 0. But in between, you get fractional powers like epsilon to the 1/2 or 1/3 or whatever. So that's the basic situation for analytic continuation if you know your functions are bounded. Now, if you ask, where does this come from in complex analysis? Well, the answer is the Hadamard three circles theorem, which goes back 100 years or so. The picture there sort of shows what's going on here. Let's suppose we have the simplest case where omega is a big disk and E is a small disk. And suppose we know that f and f tilde agree to epsilon on the small disk, and they're bounded on the big disk. Then what can we infer in between? And the Hadamard three circles theorem gives you a formula that tells you, depending on the radius, you can infer different fractional powers of epsilon. And here's how the argument, well, here's how the result goes. I like to think in terms of digits of precision. Suppose you know f to d digits on the inner circle, you know it to 0 digits on the outer circle. Well, in between, you know it for some number of digits that's between 0 and d. And the reason I like to talk about digits of precision is not just that I'm a numerical analyst, but this is the easy way to think about logs. All the theorems involve logs. So that means, in effect, they all involve digits of precision as opposed to just absolute errors. So Hadamard tells us if we have d digits of precision on the inner circle and 0 digits of precision on the outer circle, then in between we have known numbers of digits falling off from d to 0 as the radius increases. Now, to prove that, it's the maximum modulus principle for harmonic functions. I won't go through that, but it's an elementary theorem. Once you look for it, it's easy to prove. It's the maximum modulus principle for harmonic functions. Now, all of this stuff, like most of complex analysis, is conformally invariant. So once you know what happens on a disk from the Hadamard three circles theorem, you know in principle what happens on other domains. And I think the most interesting other domain is this one. Suppose you have an infinite half strip, a half infinite strip. And suppose you have a bounded analytic function in that strip, and you know it to accuracy epsilon at one end, then how accurately might you know it at other points along the midline of the strip? And well, you can see from the picture, the answer is pretty gloomy. So as you move along a strip, you lose digits at an exponential rate in some sense. So you go a certain distance, you've lost 9 out of 10 digits. You go the same distance again, you've now lost 99 out of 100 digits, and so on. And the number is here. The number of digits of accuracy falls off as you go down this strip exponentially. You lose, your number of digits goes down by a factor of 10 each time you move a distance 1.47 along the strip. Isn't that amazing? And so it's a strip of width 2. 1.47 is less than the width, and yet you've lost 9 out of 10 digits. So that's what, well, that's a sharp theorem, actually, under the given assumption that all you know is you've got a bounded function with epsilon accuracy at one end. So spectacular loss of accuracy. So here's how I, as a numerical analyst, like to say it. This is a beautiful example of a problem that's well posed, but has an infinite condition number. And let me remind you what that means. And of course, Hadamard was the guy who invented well-posedness. So well-posedness means that if you perturb the data slightly, then you still have a solution, and it also perturbs slightly. So it's a continuous map from data to solution. On the other hand, a finite condition number means not only that it's continuous, but it's Lipschitz continuous. So the condition number measures how much the answer can change relative to how much the data changed. And analytic continuation has an infinite condition number, but is well posed because of these fractional exponents. You know, losing 9/10 of the digits means you're not Lipschitz continuous, you're merely continuous. So this is my favorite example of a problem that's well posed but has infinite condition number. Numerical analysts, of course, tend to use these terms, well, ill-posedness and infinite condition number sloppily and equivalently, but when you're thinking carefully, there is this distinction. I'm always happy to be interrupted by questions. So I think we all gave talks during COVID, and I haven't done many of these since COVID. And I have to say, I really hate it because I have no idea what you guys are up to. I can't tell if you could hear me. I see Emily smiling or chewing, but it's really weird. So by all means, interrupt if you like. Are there any questions? Okay.
I don't have a question, but I'm sorry you think it feels weird. That's all.
Well, you all know what I mean. We've all been there. Okay. Just a variation on this theme. Suppose you have a function that you know is analytic, but not at 0. At 0, there's a branch point. And to be precise, suppose it's analytic and bounded in the punctured disk of radius between 0 and 2. Now, as we all know, analytic continuation allows us to go around the origin and get back to where we started. So, for example, if we have the function log of z, then the result will change by 2 pi I. Or if we have the function square root of z, the result will be negated. So, speaking in general, suppose you have a bounded function and you do this. how much accuracy have you got when you go around the circle? And the same kind of reasoning gives you an answer. So how much accuracy do you lose when you go once around the unit circle? And the answer is your number of digits is divided by 15,000. Isn't that incredible? So, and this is assuming you're calculating perfectly, doing the best possible work you could possibly do. The reason is that pi over 4 times e to the pi squared is 15,000. I won't go into it. But basically, this means that the wonderful theoretical idea of going around a circle by analytic continuation has really no relevance in generality to numerical analytic continuation for merely bounded functions. Or to put it more positively, if you can go around the circle and get anything useful, then your functions must have more structure than mere boundedness in that sense. So I think that's the end of my gloomy theorems. And as I showed on the first page, these are in a paper I published 4 or 5 years ago. So I now want to talk about the dual of the gloomy theorems, which is kind of cool. So I call this fat branch cuts or blending functions. So the gloomy view is that if you try to do analytic continuation with information at an incredible rate. But the dual of that is that if you have 2 analytic functions on different domains and you want to blend them together, you can do that with incredible accuracy. So let me be specific. Well, here's a picture indicating what I have in mind. Suppose you have an analytic function f1 somewhere and another analytic function f2 somewhere, and there's a region in between which is free for you to fix as you like. So the question is, how might you connect the one on the left to the one on the right? You can see my flavor of a fat branch cut. So that big blue box is a branch cut, but a very thick one. I want to get from f1 to f2 in as sensible a way as possible, and I'm allowed to do whatever I want in the blue box. So we've all used ideas like this in various contexts, in analysis or in complex analysis or in signal processing. Some of the phrases that we know are blending functions and bump functions and mollifiers and partitions of unity. All of these involve things like this. So now I want to tell you my favorite function. My favorite function, I'll call it tau of x, is the hyperbolic tangent of pi over 2 times the hyperbolic sine of 3.2x. Now, I'm sure Grady knows why this is my favorite function, but probably the rest of you don't. What a weird function is this? And in particular, 3.2. What in the world is going on there? How can anybody's favorite function have
Interested in interrupting you.
Oh, yes.
Grady, do you know?
Yes.
I've forgotten. So remind me, Nick, why I would know this. So
because
I've seen this many times, but now I'm trying to remember where it came from.
You'll remember in the next minute or two, but I've told most of my friends who've visited me about this function. Any other questions? Okay. By the way, just a digression on the subject of Grady Wright. He arranged a sabbatical at Oxford, and I very enthusiastically told him to come, and then I forgot he was coming, and I was off at sabbatical myself. So it's kind of a miracle that our relationship is as good as it is, but somehow we patched it up. Okay, why is this my favorite function? Well, first of all, this is what it looks like. So it's a transition function that goes from about -1 to about +1. That's the hyperbolic tangent acting. But here's what's incredible about it. In IEEE arithmetic, it is exactly -1 when x is less than or equal to -1, and it's exactly +1 when x is greater than or equal to +1. So it's, if your fat branch cut extends from -1 to 1, this is perfection. It's an analytic function that in IEEE arithmetic perfectly blends from one thing on the left to another thing on the right. By the way, if IEEE arithmetic used 62 bits instead of 64, then we could change 3.2 to pi, and it would be much more beautiful. But of course, in a deeper sense, that would be awful because it would suggest it was mathematically motivated when in fact it's floating point motivated. So please make note of that function and just think about it and try to remind yourself why I love it so much. So this is our happy duel of gloomy theorems. Suppose you want to analytically continue from one function. Oh, I'm sorry, I'm saying this wrong. I say here, imagine trying to analytically continue tau. So suppose you knew tau on the interval -2, -1. Well, in floating point arithmetic, all of the exactly 1. You then try to continue it to 1, 2. There's no way you're going to know that it actually takes the value +1 there, but it does. So this is an example of how you can connect two different things. And of course, you can use it to do more general stuff. So for example, if we have a sine wave on the left and a constant on the right, we can use the blending function to get a function like this. And so just to be precise about what I'm doing here, when I do things with my favorite function to blend F1 and F2, I'm ending up with something that is exactly analytic, but only approximately matches the data. But it matches it to a spectacular accuracy. There are various versions of this, various details, so they don't all have the same properties, but you can see that this is a nice way to blend functions. People try to do stuff like this numerically, but rarely do they kind of think of the numerics. So if your student asks you for a C infinity function that is not analytic, you will always tell them e to the -1 over x squared, right? That's what we all know about. And of course, conceptually, that's nice and simple, but numerically, it's not so great. So my numerical point here is that when you're actually working with things like this, it's worthwhile thinking a bit about what a good function is that's C infinity, but not analytic, or whatever properties you want. Any questions about that? Okay, I don't think this has been actually used that much, but I like it. Oh, that's the end of my happy duel. Okay, so now I want to become more numerical and show you some experiments which are quite encouraging. Now, a lot of you know, I'm sure, that my focus in recent years has been rational approximation, and in particular, the thing that I call the AAA algorithm, which originally stands for Adaptive Antulas Anderson. So we have an algorithm that makes it essentially easy to approximate any old data by a rational function. And I've spent a lot of my last few years working on how to use such an algorithm to do things numerically. And this talk is about one such application. It's about numerical analytic continuation. And it's remarkable, in view of how gloomy things are in principle, it's remarkable what you can do in practice. So let me show you a bit of that. So as I say, in practice, rational approximations are often quite good methods for analytic continuation, and you can compute them by this AAA algorithm. The original paper is by me and Yuji Nakatsukasa and Olivier Set in 2018. So there are lots of methods out there for analytic continuation, and of course, each one is best in some context. But I think if you want a general purpose one for numerical analytic continuation, this seems to be the best we know. Here's a typical easy picture. Suppose I take the gamma function and I sample it at 30 equally spaced points on the unit interval from -1 to 1. So you can see in this picture, data indicates these 30 sample points for the gamma function. And suppose I then want to estimate the gamma function outside the interval. Well, the simple approach is to simply fit it to standard machine precision, or more precisely, 13-digit precision, by the AAA algorithm. So you have a rational function that agrees with the gamma function to 13 digits on the unit interval. And then here you can see a plot of that same rational function outside the unit interval. And I'm sure we all know the gamma function. It kind of looks like this. So you can see the rational approximation has captured the first couple of poles to the left of the unit interval at -2 and -3 to pretty good accuracy. And then beyond there, it doesn't capture any more poles. The thin black line is the actual gamma function, and the red line is the rational approximation. So this kind of thing is, in some sense, old hat to physicists who do it with pas-de approximation. What's new now is that it's so easy to do it based not on a Taylor series, but on a set of data points. Now, Jonathan Smith has raised his hand.
Yes.
What-
Is this what MATLAB does?
No, MATLAB doesn't have AAA. If you try to do this in MATLAB, you'll fail.
But I believe they do use rational functions, don't they, for everything?
Well, as it happens, the AAA algorithm is now in MATLAB in 3 of the toolboxes: the RF toolbox, the signal processing toolbox, and the control system toolbox. But in core MATLAB, I don't think there's any way to do this.
Okay, thanks.
In particular, if there are any RF toolbox at MATLAB, which stands for radio frequency, they're basically their central tool is now the AAA algorithm. Another example. So this is the zeta function, the Riemann zeta function. Now we're in the complex plane, and I've imagined that I have sampled the data function at 100 points with real part +4. And as I'm sure you know, the zeta function is easy to evaluate in the right half plane, or more precisely to the right of real part 1. And it's not so easy to evaluate elsewhere. But here what we've done is we've taken these 100 data values, and then in a half a second, the AAA algorithm finds a rational function that matches them at those 100 points to 13 digits. And then the plot shows a so-called phase portrait of this rational approximation. The colors show you the complex argument. So red is positive real and cyan is negative real, and the other colors are in between. So you can see this stripy picture, which actually, that part of the picture looks just like the actual zeta function. So the rational approximation has captured a lot of the structure of the zeta function. And in fact, if you look along the critical line there at real part 1/2, you can see a lot of zeros in the plot. And these match the actual zeros of the zeta function to 7 or 8 digits. So the remarkable thing here is, first of all, showing the power of rational approximation to find things, but computationally, the idea that it's effortless to compute this stuff. It takes half a second on a laptop in MATLAB to generate this approximation. It's just really, really easy with the AAA algorithm. Before AAA, it would have been a master's project to find an approximation like this. There would have been no obvious algorithm. Of course, people could have done it by some kind of optimization, but it would have been really hard. Any comments or questions?
I have a question, Nick.
Yeah.
Is the samples you took somehow collected into like batches of 6? I'm just trying to understand the pattern I see of how you sampled the function, and if that was important.
Yes. I see that on my screen too. That's just MATLAB graphics.
Okay.
They are equally spaced.
Equally spaced, yeah. Okay.
Any other questions? But Grady, I like the way you think. I'm the same way. If I see anything in a plot, I always ask the person. And what you usually find is that the student hasn't actually thought about their own plot very much. So I try to teach them, when you produce a plot, think about it. Okay, here's another example. So here I took, in the black part of the curve, that's a bit of a Lorentz equation trajectory. So, you know, the Lorentz equations are a system of 3 coupled ODEs. Here I've taken a solution, and I've taken one of the 3 components and plotted it in black. If you actually extend it, I mean, the actual solution extends beyond the black region in the blue line. But suppose we sample those black points in 100 or 200 points and then do AAA approximation, and then evaluate that rational approximation outside the black region, then you get the red part of the curve. So you can see there that numerical analytic continuation is doing something useful. It's getting us sort of about 1 wavelength of somewhat accurate analytic continuation. And this is the 1 wavelength principle that I'm going to talk about some more. So the rule of thumb is with AAA, we can usually get about a wavelength of analytic continuation numerically. Here's another example. I'm in 2 dimensions. This is just a real function in 2 dimensions. It's a Hankel function that satisfies the Helmholtz equation. I've sampled the function with y equals 0 and x between -1 and 1. So that's the black part. So I've sampled in a few hundred points on that black interval. And I'm trying to extrapolate along the x-axis from those sampled data. And in the plot below, you can see the sampled data are in the interval -1 to 1. The true extrapolation would be the blue, and the AAA approximation is the red. So again, we're getting 1 or slightly more wavelengths of apparent accuracy.
Hey, Nick, do you have any intuition for what sorts of functions want to be approximated by irrational functions?
Yeah. Well, of course, analytic is great, but they don't have to be. C infinity does surprisingly well. I used to think that the right answer was band limited, but that turns out not to be the right answer. So at the moment, we don't have a very clear thing to say about that. Here's another very similar example, except now instead of extrapolating on one line, I'm extrapolating on a lot of lines. So on the left, we have a really trivial function, sine of 2x plus y in the xy plane. And on the right, we're imagining that we try to extrapolate from the left quarter of that picture into the right 3/4. Now, we don't know how to extrapolate in 2 dimensions. All we can do is 1 dimension. So what we do is we extrapolate on each of 100 different lines. So the black dots are the sample points. And in a fraction of a second, we do about 100 AAA approximation problems to extrapolate along each horizontal line. And you can see that in this case, we have 1 or maybe 1.5 wavelengths of successful extrapolation. Here's another example. One of my favorite functions, because it's so simple, is the square root of x squared plus y squared. Now, of course, we know what that function looks like. It's just, concentric circles. But suppose we try to do that numerically, again, extrapolating from the left to the right. Again, I don't know how to do the whole problem in a bivariate fashion, so I reduce it to 100 univariate problems, 100 horizontal lines extrapolating from 20 data points. And you can see, well, it's kind of interesting, but of course the singularity at the origin kills us. And, is it good? Is it bad? I don't know, but this is what we can do. Here, in case you are interested in pseudospectra, an old interest of mine is a similar picture for pseudospectra, which again is a real analytic function with some singular points corresponding to eigenvalues of a matrix. Here's another similar picture involving eigenmodes of a drum. So we're on an L-shaped drum. And in each of these 6 pictures, I've taken the eigenmode in the L-shaped drum, and I've tried to extrapolate it north from the bottom right leg into the upper right quadrant. And you can see that AAA is doing a pretty good job. It's extrapolating on these white lines. So in each case, I'm doing a few dozen AAA analytic continuations. The pictures look good, except where the singularity messes you up at the re-entrant corner. The third mode is special. You notice the singularity doesn't mess you up in that case, and the reason is there's no singularity for the third mode. It actually reflects by the Schwartz reflection principle to a globally analytic eigenmode. So you can see that you can get some compelling pictures numerically using AAA in 1D and 2D to do numerical analytic continuation. Now, where are we here? Here's another version of pretty much the same. And this is something that certain people doing numerical PDEs are interested in. And in fact, Grady, you're probably in this game too. So many people have asked, what if you have a analytic function defined in some domain, and you want to extrapolate it a bit outside the domain for numerical reasons that I won't go into? There's a picture from a paper by Strickland, Leto, and Tornberg. Well, it turns out AAA is pretty nice. So in this case, the pair at the bottom there, I take my data. Again, it's a 2D problem, so I can't do one extrapolation. I have to do lots of 1D extrapolations. So I think we have 80 radial lines there. And on each of those 80 radial lines, I sample the function. I do a AAA extrapolation. And then in a fifth of a second on a laptop, you get the picture that I show you there. Notice it's about one wavelength of successful extrapolation. And I think
Nick?
Question, yes.
Oh, yeah, there's a question in the chat. It says, it's from Victor Miller. He says, if you're restricted to one-dimensional extrapolations, what about using a parameterized family of curves?
Yes. I haven't thought of a way to make it work, but it might work. If you have a way to do that, I'd love to hear about it. So yeah, maybe that's a great idea, but the practice is what kills you. I don't know. What I'm doing here is not that. It's just completely independent approximations on each line. Other comments? I think the next slide is on some more recent work. So there's a very nice paper by Epstein and Strickland and Jiang that just came out on this function extension business. And it's very interesting to think about that kind of approach compared with AAA. So if you just look at accuracy, AAA seems to get sort of one wavelength as opposed to two wavelengths. So, sorry, as opposed to half a wavelength. So here we have a picture from their paper showing function extension from the blue to the red. And then AAA, you can see, gets about twice as far successfully. And similarly, they have a two-dimensional picture showing extrapolation outside a disk. And again, AAA gets about twice as far. Now, so what's going on here? AAA is a rational nonlinear method. What they're doing is a linear, much more robust method. AAA in principle is giving you different extrapolations along every direction. So mathematically, what AAA gives you isn't even continuous in the tangential direction, although it would be continuous to many digits of accuracy. Whereas the function extension people prefer methods which are less accurate in some sense, but also more robust, and they are continuous. So they're kind of using the same formula in all directions. So which is better? Well, it would depend on your application. If you just want accuracy, I think AAA is clearly better. But for an application for solving PDEs, they would argue that a more robust formula is better. Okay, finally to the other part of my title, the one wavelength principle. And just to remind you at the end, if there's a moment, I'm going to show a couple of demos. I've already alluded to the one wavelength principle. In fact, going back to the last slide, you can see it there. In the bottom row, each extrapolation is sort of getting you about one wavelength of accuracy. So what is this principle? Well, experience suggests that in 16-digit arithmetic, it's possible to analytically continue an oscillatory function about one wavelength beyond its sampling domain. Now, what in the world does that really mean mathematically? We don't know, but let me show you a little more about it. So here's another example where we're just extrapolating the cosine. The picture above is showing you in the complex plane the AAA approximation to the cosine, which has 14 poles, 7 in the upper half plane and 7 in the lower half plane. And then the picture on the bottom is showing you just along the real axis the extrapolation from a certain interval left and right. And you see it sort of looks like about a wavelength. More precisely, well, not really more precisely. It looks more precise, but it's still very hand-wavy. What we seem to find is that we can get about 0.075 wavelengths per digit of AAA approximation. And here's some evidence for that. So this picture was computed by Don Huybrechts in Leuven. He's taken two different functions here, the blue one and the red one. And in each case, in Julia, which makes it good for extended precision, he's approximating the function to more and more digits using AAA, and then measuring in some principled fashion the number of wavelengths of extrapolation. And you can see this pretty clean relationship that as you get more and more digits, you get more and more wavelengths. So 13 digits gives you 1 wavelength, 26 digits gives you 2 wavelengths, 39 digits give you 3 wavelengths, 52 digits gives you 4 wavelengths. It's kind of cool. So of course I would like to prove this theorem, but it's not a theorem yet because, I mean, it's not a conjecture yet because I don't know how to formulate it. How do I make the notion of wavelengths precise? I have to tell you, we're not going to succeed. I tried and haven't succeeded yet. If one of you can do it, I will be very happy. So we don't have a theorem. We don't even have a precise conjecture. We have some hand-wavy arguments that make it plausible, which I won't go into. In the literature, the only paper I've mentioned that sort of seems to come close to this is by Henry Landau at Bell Labs in 1986. Now, some of you may know him, but others don't. But back in the great era of Bell Labs, there was this incredible trio of guys, Landau, Slepian, and Pollack, who wrote a succession of half a dozen amazing papers going back to the 60s, really. They were the ones who did prolate spheroidal wave functions, but also they were the ones who put the idea of band-limited functions on the map. It's just really outstanding applied mathematics from Landau, Slepian, and Pollack. And the only paper I found that seems to come close to the one-wavelength principle is by Landau 40 years ago. And this is a quote from him. He says, "When sample measurements are accurate only to within epsilon, good extrapolation is possible for only a bounded distance, having an order of magnitude log epsilon beyond the interval of observation." So that's just it. It doesn't, but that is suggesting that this logarithmic relationship between precision and extrapolation, or linear relationship between number of digits of precision and extrapolation. Now, unfortunately, if you unwrap the proof of his theorem, which you can do, I mean, he's wonderful. The paper does give a very clear argument. The argument only goes in one direction, not in both. And so I won't go into the details, but it doesn't give us what we need. And moreover, well, sorry, I haven't written this on the slide. I thought we could push Landau's argument somehow by analyzing band-limited functions and stating theorems about that. But then a brilliant graduate student at MIT called Alex Cohen showed I was wrong. And in fact, Landau's theorem, although correct, is only correct in one direction. Well, it's not really the case that band-limited is the right condition. So although he doesn't use that phrase, it's all about band-limited functions. It turns out that isn't right. And a theorem proving that band-limitedness is not enough was proved by Alex Cohen, and you can find it in my column in the notices of the AMS a few months ago, called Unbounded Growth of Band-Limited Functions. So Alex Cohen has proved that my attempt to make sense of the one-wavelength principle by band-limited functions does not work. So I'm left not knowing what to do. So if any of you are curious, please take a look at that notices column. I think it's from January, and I'd love to learn more. Now, I still have a few minutes, so can I show some demos? But first, are there questions? Okay.
I guess I have two questions. So you've mentioned a couple of times that this is based off of one-dimensional functions, and in the machine learning community, there's been this recent surge of interest of like an old theorem of the Kolmogorov-Arnold representation theorem, that it takes a multivariate function and it shows that it can be expressed as compositions of sums of univariate
Yes.
functions. Have you
Yes.
thought at all about whether or not there's something to do with that?
I mean, what a fascinating question. So I don't know how many of you have seen that theorem, but it's a brilliant, surprising theorem. Though if you unwind it, the univariate functions involved are insane. I mean, it's really a million miles from application. I'm kind of prejudiced. I think maybe you can do something, but that it won't have much to do with that theorem. That's my instinct, but I don't know. If I may say a word about machine learning more broadly. It's not a subject I know much about. You know, our whole world is being turned upside down by AI, and mathematically, that's very much about approximations of functions in neural networks. The approximations are not rational, although they could be, but as it happens, you don't even need rational. You can just use our ReLU function. But what they are is multi-layer, so they're composite approximations, and they're multivariate. So in some sense, it's possible that the human species is going to go extinct because of the power of approximation theory, because the rate at which AI is getting powerful is really scary, as I'm sure we can all agree. If that happens, don't worry, we won't know what happened because none of us really understand the approximation theory very well anyway. But something about multivariate recursive nonlinear approximation is driving the AI revolution. Now, what I'm doing is univariate and monolayer. So I'm a long way from that. I'm not going to make anyone go extinct. But it is really intriguing to realize how our world is being changed by approximation of functions. I'm at Harvard, so I think at every place on Earth, machine learning is big. But Harvard has taken this to the limit. There's nothing at Harvard except machine learning apart from me. So I'm it. All the other scientists at Harvard are doing machine learning, and it's pretty impressive. Of course, I slightly exaggerate. So I do want to show a few demos. So I have 5 functions I will execute in MATLAB. And you've seen them all already. Well, you've seen most of them already, not all. In the last one, there's actually some data that I'm feeding in, not from MATLAB, which is from Toby Driscoll in Julia. Oh, so but I should say a word about Toby. So as you perhaps know, he's at University of Delaware, and he's quite amazing. In fact, since I have a minute, let me mention several things about the astonishing Toby Driscoll. First of all, anyone who does Schwarz-Christoffel mapping for the last 40 years uses his software. It's the Schwarz-Christoffel toolbox. Second of all, anyone who teaches numerical analysis needs to know about his book, which is in Python, Julia, and MATLAB, and freely available by Toby Driscoll and Rich Brown. So I'm sure some of you are teaching numerical analysis, so let me tell you slowly the website to find it. It stands for Foundations of Numerical Computation, so it's fncbook.com. fncbook.com. If you go there, you will find a freely available textbook that's really a good textbook of numerical analysis in Python, Julia, and MATLAB. Toby's the person I know who has thought most carefully about the relations between those 3 languages, and you'll find right at the beginning of the textbook some interesting discussion of that. The third thing I wanted to mention about him connected with this talk is that he has wonderful Julia implementations of both the AAA algorithm as I've been showing it to you, and also the adaptive continuum mode AAA algorithm. So if you want to do AAA in Julia or MATLAB, go to Toby's website at the University of Delaware and you'll find some good stuff. Okay, so I want to show you these 5 demos. So I'll switch over to MATLAB if I can. Can people see a MATLAB screen?
Yes.
Yeah, okay, great. So the first one is called extension, and this you've seen a picture of. That's misspelled. It's extension, right. So just as I showed you, imagine we have a domain inside of which we have an analytic function of 2 variables. So it's a bivariate function of x and y. In order to extrapolate outside this domain, I'm going to sample the function on radial lines. And here's the function. And this is all running live. So when I press return, it's going to do, I think, 80 AAA approximations and then plot the result, extrapolating along each of these 80 lines. And the point is just to illustrate how fast it goes. So I will press return. The 3, 2, 1, go. There's your picture. So 80 AAA approximations giving us nice one wavelength extrapolation. It's just so cool. It really works. We have no theorems to prove it'll work as well as it does, but it's really reliable. The next example is called Lorentz, and you've seen a version of that. So in this example, I compute a little bit of a Lorentz trajectory. I think it's the same one you already saw. And this is something new. In the lower picture, I'm showing you in the complex plane the poles of the rational approximation to that Lorentz trajectory. So we match the function to 13 digits. That's a rational function of degree, maybe 30 or 40 or 50. And then we plot its poles in the complex plane. And you can see that there are a bunch of poles which are not on the real interval, but getting close. And indeed, they get closest at the peaks of the Lorentz trajectory. There's a bunch known about this theoretically. The actual mathematical analytic continuation into the complex plane doesn't involve just poles, it involves branch points. So what you're actually seeing here are some poles approximating branch points. If I keep going, pressing return again, it highlights part of the trajectory in black. And then it does AAA approximation from the black part, left and right. So you can see again, sort of one wavelength of accurate approximation, accurate extrapolation. Any questions? Okay, the next one is called Burgers. So the Burgers equation is a nonlinear PDE, in which shocks form. Now I'm doing the viscous Burgers equation, so it won't be a completely sharp shock. If you look on the left here, you see that when time elapses, we get a shock that steepens up and then it weakens because of viscosity. Let's run that again. So there's the initial condition. It steepens up and then it loses amplitude because of viscosity. But then if we look at the picture on the right, what we're doing is at every time step of the simulation, I'm giving my blue curve to AAA and computing poles in the complex plane. So again, this illustrates how fast AAA is. You can actually do it at every time step of a simulation. So the poles start at infinity and then come in towards the axis and then go out again. And every time it moves, that's just another time step of a simulation. People are interested in curves like this, like Burgers' equation or the Lorentz attractor, and how they extend into the complex plane. I personally am not as persuaded as some people that really captures the essence of the matter, but it's certainly a mathematically interesting problem. Stop me if there are questions. The next demo I haven't hinted at all, and it's a whole new analytic continuation topic with resonances in many directions, which I call Schwartz. So Schwartz, of course, was the great figure in the around 1870 with the Schwartz-Christoffel formula and the Schwartz reflection principle and so on. And he was interested in reflection of analytic functions across curves. Now, you all know if you have an analytic function that takes real values on a real interval, then reflection is trivial. But what if it takes real values on an analytic curve? Well, Schwartz figured that one out too. And the way it's done is with something that people now call the Schwartz function. I should go back, but I can't. So the Schwartz function is this incredibly simple definition. And the definition comes from Phil Davis, I think, in around 1959 or something. You have a curve, the black curve, and you simply take conjugate of z on that curve. So you take the function f of z equals conjugate of z, complex conjugate of z, and you analytically continue that function off the curve. And that turns out to be the key to reflection across analytic curves. So there are a couple books on this subject and a few papers, but I believe there has never been a numerical computation of a Schwartz function before AAA. But AAA now makes it very easy. You have your black curve, you evaluate the conjugate of z on that curve, and then you just approximate it by a rational function. We've done that here, and the dots indicate the poles of the approximation inside and outside. So what you're seeing here is evidence that the Schwartz function for this curve has branch cuts, both inside and outside. If I press return, it gives you some indication of the accuracy of our numerical approximation. So the dark green means that we've captured it to 8-digit accuracy, and the light green means that we've captured it to 1-digit accuracy. And how do we know how accurate it is, since we're the only people in the world who've ever computed the Schwartz function? Well, the answer is the Schwartz function is supposed to reflect you across a curve. So you reflect across and then back again. And if you come back to where you started within 8 digits, that's 8-digit accuracy. So it's kind of fun that here we have the first method ever to compute the Schwartz function, and it really seems to work. And it gives a lot of insight. Here you can see a phase portrait of that same thing. And you notice how the branch cuts that are delineated by poles correspond to changes in argument. So it's really the case that a lot of rational approximations are approximating branch cuts numerically. I'll run this again because it'll be another random curve. There's another random curve. What's the Schwartz function? We do AAA approximation of conjugate of z, and we get poles inside and outside. We check the accuracy, and we can see that it's 8-digit accuracy on a nice strip, but there are a bunch of branch points. And as usual, there are some branch cuts approximately delineated by the poles of the approximation. So I'm all focused these days on branch cuts and quadrature formulas, and I would love to talk for another hour on that subject. There's one more demo. The last one is called one wave, getting back to the title again, the one wavelength principle. So I think this one is going to show you 6 functions, and this is the one with canned input. I don't know if you can read that. The font is very small unexpectedly. This is the function sine of 3x on the interval from -10 to 10. And we're supposing that we know the function in the interval for -x. And based on that information, we want to extrapolate to +x. And of course, we do it by fitting by AAA and then plotting the rational fit. So when I press return, you'll see the red line is what you get if you do this to 13-digit of accuracy. And the black line is what you get if you do it to 26 digits of accuracy. And those two approximations have rational degree 20 and 29. So roughly speaking, we get 1 wavelength from 13 digits and 2 wavelengths, or maybe 2.5, from 26 digits. And now I have 5 more examples. Here we have a function. What is it? I can barely read that. I hope you can read it. The trouble is screens keep changing and fonts keep changing. -1 plus 1 over 1/5 plus the cosine of 2x. Okay. Again, we sample it on the left and we extrapolate to the right. With 13 digits, we're getting 1 and a bit wavelengths. With 26 digits, we're getting 2 and a bit wavelengths. There's a third function. So it's 0.2 times e to the x over 4 times the sine of 3x. With 13 digits, we get that. With 26 digits, we get that. All these computations done with Toby Driscoll's Julia package. Here's a function that doesn't have a regular wavelength, but irregular. It's cosine of 2 times e to the x over 3. So it's getting faster and faster. I guess electrical engineers would call it a chirp or something. With 13 digits, you get there. And with 26 digits, you get there. So you can decide whether that's 1 and 2 wavelengths. Here's the cosine of x to the 4th. With 13 digits, you get there, which is certainly less than a wavelength. I'd call that a half a wavelength. With 26 digits, you get there, which is a little more than 1 wavelength. And here's the hyperbolic tangent of 4 times sine of x. With 13 digits, you get that, which is less than half a wavelength. And with 26 digits, you don't do much better. I'm showing you that just to be honest. You know, we don't have a theorem. The one wavelength principle is not always as simple as the name suggests. So I think I'm done. You can see how much fun I have trying to mix a bit of theory with a lot of numerical computation. Thank you very much.
Yeah.
I guess I forget Mike is gone, so I will finish this up. Let's smash that reaction button. Looks like most people are already doing that. Do we have any additional questions?
I do have a question.
I'm trying to. Yeah.
My question might be stupid because think about me as an undergraduate student who doesn't know anything but who's curious.
Okay, I'm trying to stop sharing and I feel equally ignorant. How do I stop?
No, that's fine.
Yeah.
So when you said about one wavelength, I was trying to follow your presentation, but the one wavelength really doesn't have a definition then. It's just kind of like a feel of what you see.
Yeah.
I was trying to figure out like what kind of wave are we talking about? I mean, a lot of the pictures you showed had waves, but
Yeah. I would love to know an answer to that. As I sort of hinted, I thought the answer might come from band limited function theory, but that doesn't work. So I'm open. I would love to have an answer. It's an open research problem. If I make another comment about AI, AI is very good these days at solving hard math problems that are perfectly well posed, the sort of thing that you give in an Olympiad. But AI, I don't think is yet very good at my kind of math problem, where the real challenge is, what's the question? You know, how do I formulate this one wavelength principle in an intelligent way? I think AI is still useless at that. Now, give it another 5 years, of course, it'll probably be better than we are. But for the moment, we need a human being to figure out how to make the question precise and then prove the theorem.
thank you.
Other questions for the speaker? Jonathan Smith.
Yes, may I make a suggestion to maybe rehabilitate AI? The example you showed with the radial symmetry, trying to do the circles.
Yeah.
Okay, your AAA went bad on you because it didn't recognize the symmetry. But AI could quickly recognize the symmetry. So if you can talk to the AI people, you could get, and now I'm going to trademark this, AI. That's a very good algorithm.
I presume you haven't tried it, but that's a fascinating idea. Yeah. Yeah, it's amazing what's coming down the pike. I don't know about you, but 6 months ago I used AI once a month. Now I use it several times a day. It's quite astonishing.
Great, you're right.
Yeah. Hey, Nick, great talk as always. But I had a question if any progress has been made on the case where the